Hey, what's up, Math 1? Mr. Bain here, and we're going to take a look at lesson 14.4, graphing exponential functions. We've finished one lesson where we're looking at how exponential functions work, doing a table of values, we're plugging in our inputs, getting outputs or know how to get outputs, and then graphing them just to kind of see what they look like on a graph. So in this lesson, we're going to dig a little bit deeper and we're actually going to make the curve and learn the shapes of these things. And so this is a fairly long lesson because we have 4 different shapes of graphs. And I'll be going through each and every one of those, and I'll be asking you to try a few for yourself, just so you can practice a little bit. So the first thing I want to show you is this resource. If you don't use it very often or you don't know about it yet, Desmos, Desmos, is one of the more well-known and powerful calculators, graphing calculators for that matter, in the math world. And it's also a calculator that gets used, whether it's just a regular calculator or graphing calculator, on the SBAC test. And so they use pretty much the same software, same company. So it pays to it helps at least to get familiar with how to use this. So I'm gonna type in the functions that you see right here. So you see y equals 3 times 2 to the x. You'll see me type that in to the Desmos calculator. I'll type the others in as well. So y equals 3 times. I'm gonna speed this up a little bit so you don't just see me struggling to type all this stuff in. And here we have the 4 graphs. You only see one of them on the actual screen because the left side of this, there's no color here in these 3 circles. So you can toggle them on and off if you have multiple graphs on here. Again, this is a pretty powerful tool. You could download the app for it. I have it on my iPad, my iPhone, or you can just open it up in a browser. It's pretty user friendly in that way. So the red graph that you see is the shape of the graph for this y equals 3 times 2 to the x. And let's look at another one. So there is the second one, if I can get it to work, the blue one. 0.5 times 2 to the x looks like that. And you see it looks, I mean, it has the same, I would call this the same shape, or at least when we start talking about end behavior, it has the same end behavior. It's going the same way, okay? Here's the green one. You can see it's going a different direction, has a slightly different shape to it, okay? And the purple one, okay, it's in a different place, has different end behavior, different shape to it. Now this, now actually they have pretty much the same shape. It's the end behavior that I'll talk more about. And so, yeah, if you're wanting to use Desmos to check your answers as you're graphing it, I want you to know how to graph it without using this first. But this, again, is a nice, helpful tool for you. Page 679 on the bottom. Now let's look at the your turn on the bottom. We're going to graph the exponential function f of x equals 2 times 2 to the x. And after graphing, or I guess we can do it before, we're going to identify a, b, the y-intercept, and the end behavior. So I'm going to do all of that. Our general form, we can use we can use y, or we could use f of x is a times b to the x. So if I compare a times b to the x to this, then our a is that first number, our b is the base of the exponent. Okay, so to identify means to just tell you the value of these. A is 2, b is also 2, and the y-intercept means when x is 0. The y-intercept is, we've actually done this in class before, that will always be the a value all the time. All right. I'm going to talk about end behavior after we actually graph this thing. So I'm going to draw a table of values. I'm going to erase it after we actually get some points. But this is sort of the more basic way to get some points and figure out the shape. Eventually, I don't want you to make a table of values all the time. Just like with making a line, we don't have to do a table of values. We can look at slope or y-intercept to get our line. And that's, again, that's where we want to head. So let's just choose some values that we could use. I'm going to do 5 inputs. If our input is -2, that means 2 times 2 to the -2. Okay, so you gotta do the exponent first. 2 to the -2, that's gonna be 1/4, since the negative means reciprocal. 1/4 times 2 is gonna be 1/2. Okay. 2 times 2 to the -1 is just gonna be 1. 2 times 2 to the 0 is gonna be 2. Remember, we already established that the y-intercept is 2, so it makes sense that it has to be 2. But if you needed further convincing, right, just plug it in. 2 to the 0 is equal to 1, and multiply that with 2. 2 to the 2, sorry, 2 times 2 to the 1, and 2 times 2 to the second are our last ones. So this is going to be 4, and then looks like 8. If I graph this, and the scale on this is really weird. It goes by ones on the x-axis, but it goes by 1.5s on the y-axis. Be careful and make sure you're accurate. -1 is going to give us 1. 0 is 2. 1 is 4. 2 is 8. And 5 points is a good number for us to get because it's going to give us enough points to know, wow, that's really bad, to know the shape of this thing and the direction of it, or what we call the end behavior. Okay, so let me erase, let's erase our table of values and now write the end behavior. End behavior means, and we're going to start thinking with something that's used a lot in calculus. In calculus, we think a lot more abstractly, and we think in very, very, minuscule numbers, very small numbers, or very, very large numbers. We do that a lot in calculus. And so what we want to figure out is, as x, our input, as x approaches infinity. So let me write down, as x approaches infinity, or in more plain English, as x gets really big, then what happens to the y? That's what we got to figure out. And if you don't want to think in terms of x and y, think input output. As our input gets really big, remember I only used input of 1 and input of 2. What happens to the output? So just pretend, we're going to plug in our input of 3. So we're going to think, okay, 2 times 2 to the third power, then we're getting output. 2 times 2 to the fourth power, then we get an output. 2 times 2 to the fifth power, we get an output, and so on. And even go bigger, 2 times 2 to the 10th power, 2 times 2 to the 50th power, to the 100th power. Think about what's happening to the output. Is the output getting bigger? Is it getting smaller? Is it getting closer to a certain number? Right? And let me just go and give you the options, because we're not dealing with super complicated exponential functions here. y is either going to approach infinity, and that means y is going to get really big. Y is going to approach 0. So it's going to get like into the, 0 0.1, 0 0.0001. It's going to get like really, really close to just being nothing, to being 0. Or it's going to go really, really low to negative infinity. Okay, so another way to think about it is just follow along the graph, right? As you go to the right, as x gets big, you're going this way. You're going over here. As you're going this way, is this going up or is it going down? And you see it's going up, so y is getting really big also, right? 2 times 2 to the 100th power means you're multiplying a whole bunch of 2's. That's the first part of end behavior. Okay, I wanted to make sure I tried to explain that as well as I could. The second part of end behavior is as x is approaching negative infinity, or as x gets really small. Okay, negative infinity. So if you were to plug in negative 50 as our input, negative 100, negative 1000, negative 1 million, you can even try it. And what that's going to do to our base, right? Say 2 to negative 100. It's going to make it change to the reciprocal. All right, let me just show you really quick. 2 to the negative 100 means 1/2 or 1/2 to the 100. Now, 1 over a really, really, really big number is actually really close to 0. That's almost nothing. So it's one piece out of, I don't even want to think about what number this is. It's a really, really big number. But one piece out of this many pieces is, again, almost nothing. So what's going to happen here, I'll just give you the answer. As x is getting really small, our output, our y, is going to approach 0. And hopefully you can see that on a graph, that as from here you're going to the left. Yeah, the output, or the shape of this is kind of flattening a little bit. And this is never going to go below this axis. It's going to stay kind of like almost get parallel to it, but not really. It's going to get really, really small. I urge you to try to, put this on Desmos and then just kind of zoom in to this part as much as you can and kind of move over a little bit and zoom in some more. And you'll see it's never going to touch, but it's approaching, right? The arrow means it's not going to equal it, but it's getting there. Okay, that's enough explaining of that. I want you to try one now. So on this page 681, number 7, do the exact same thing with this, the negative 3 times 3 to the x. Get your a, your b, your y-intercept, describe end behavior. I'm going to wait 5 seconds and then have the solution pop up. Go and pause it. And here we go, and I don't have the full solution up here yet, but let me talk you through it. Our function, negative 3 times 3 to the x, the a value is the 3, the same as the y-intercept. The b value is 3. So I know that my y-intercept is negative 3, so there it is. I did think about the inputs and outputs, so try to get some accurate points. If you plug in 1 as your input, we will get negative 9. 2 as your input gives, looks like negative 27. Okay, and so it's going to have this sort of shape. So as you can see, we start negative 3. If I do a bigger input and a bigger input, my graph is going down. And going down means, and going down to the right actually, means that our output is getting smaller, right? It's going to negative infinity. Just think about if you even just plugged in 5, right? 3 to the 5th power, and then times -3. Uh, Geez, that's going to be, 27 times 27. It's going to be negative, so it's going to be, a pretty small number. And then if I'm going backwards, kind of similar to the last one, if I'm going backwards to the left, this thing is flattening out, right? So I did plug in -1, and that gave us an output of -1. If I put -2 as my input, I'm going to get -1/3, so that's closer to 0. Then I'll get -1/9. Then I'll get -1/27, and it's going to get closer to 0. It's never going to go positive though, and it's never going to equal 0, but it gets closer. One thing I forgot to mention about this graph is that we call this decreasing. I want you to think about why before I say it. Decreasing negative. And I didn't mention it on the last graph, but we would call the previous one increasing positive, right? Increasing positive means that as you're going to the right, it's increasing, and it's positive because all of your outputs are positive. Decreasing, in this case, as I'm going from left to the right, it's decreasing, it's going down. And it's negative because all of our outputs in here are going to be negative. On the next page, 682, let's look at your turn number 9. And if you want extra practice, I would say go ahead and pause it. I'm just going to have the solution magically appear in front of you here in a few seconds. For our A and B values, you see that it's 3 and 0.5. Our y-intercept is 3. The graph has this shape, right? It starts from up here. It's going to be decreasing. If I look at the name of this compared to the other ones, we call this a decreasing graph. It's decreasing from left to right, and it is positive because all of the outputs are positive numbers. And behavior. Okay. Going to the left might be a little bit easier for us. So left means we're going to, x is getting smaller, right? Negative infinity. As we're going to negative infinity, or get our numbers, our x's, our inputs are getting smaller. The y is going up, and that means the y is going to positive infinity. As we're going to the right, and you can even think about your common ratio, which is 0.5. If I take this output times 0.5, right? The output, this is the y-intercept, this is 3. Times 0.5 is 1.5. Times 0.5 again is 0.75. Times 0.5 again is, 0.375. I probably got that wrong, but it's half of that, right? Times 0.5. Times 0.5 again is, 1.1 something. And you can keep going. It's going to get closer and closer and closer to 0. It's getting smaller, but it's like kind of slowing down. So you're going to see it's flattening out, and that means our y, as we're going to the right, our y gets closer to 0. That's the end behavior. Let's take a look at one more. On this one, this is going to be the last type of graph, right? I think we did, let's see, increasing positive, we did a decreasing negative, and a decreasing positive. So that leaves one more. You can think about what that might be, but go and pause it. I'll have the solution show up here in a few seconds. Here's our last one. It is increasing, and it's negative. Outputs are negative, but it is going up from left to right. And by the way, I didn't mention this, but knowing whether it's increasing or decreasing, knowing whether it's positive or negative, that's not really the important part. Just knowing that that's what the pattern is. And you won't have to, state what type of graph it is and all that, but you will need to know how to sketch these and how to identify end behavior or describe end behavior, identify your y-intercept, your A and your B, and all that. Okay, as we're going to the right, as x is going to infinity, y is going to 0. Okay, so if you look at my arrow, as this thing is going to the right, it's getting closer and closer to that x-axis, so that means it's getting closer to 0. As x is going to negative infinity, that means to the left, this graph is going down, and that means that the outputs, are approaching negative infinity. It's getting smaller and smaller and smaller. Okay, that's it. Thanks for sticking with this and staying till the end. Hope it was helpful to you. Have a great day.